Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into Fortune's algorithm for generating Voronoi diagrams. A treat. It's a fascinating, albeit challenging, algorithm.
I've heard whispers of its complexity. What's the big picture? What even is a Voronoi diagram?
Great question. A Voronoi diagram partitions a plane into regions based on proximity to a set of points, called sites. Think of it like this. You drop pebbles in a pond. The Voronoi diagram defines the areas closest to each pebble. It's used extensively in procedural map generation, among other things.
So procedurally generated maps, like those in games? That's cool. But Fortune's algorithm, why is it so notoriously difficult?
Precisely. The elegance lies in its efficiency, O(n) log n, time complexity. But the implementation is a beast. It involves a sweep line that moves across the plane, creating and managing parabolic arcs, called a beachline, which represent the boundaries of the Voronoi cells. The interactions between these arcs are where the complexity lies.
Parabolic arcs? Sounds intense. What are the key events that drive the algorithm?
There are two main event types, site events and circle events. Site events occur when the sweep line encounters a new site, adding a new arc to the beachline. Circle events happen when three arcs on the beachline converge, creating a Voronoi vertex. The algorithm cleverly manages these events using a priority queue.
A priority queue? So it's not just about the geometry, but also about efficient event handling? That makes sense, but how do you actually represent the beachline?
That's a clever part. The beachline is represented as a sequence of sites, with each site defining an arc. However, a simple sequence isn't enough. You need to handle cases where a single site appears multiple times on the beachline, representing different parts of its arc. A more sophisticated data structure, like a binary tree, would be more efficient. But a sequence works for smaller implementations.
I see. So the algorithm essentially tracks the intersections of these parabolic arcs, which define the edges of the Voronoi cells. And the circle events mark the vertices, where three edges meet.
Exactly. The intersections of the arcs are initially incomplete edges, becoming complete only when a circle event occurs. The algorithm also needs to handle false alarms, situations where arcs appear to converge but are interrupted by a new site event before the convergence actually happens.
False alarms. That sounds like a real headache to debug. And what about the data structure used to store the final Voronoi diagram?
The standard data structure is a doubly connected edge list, DCEL. It's a complex structure, but it's well suited for representing the planar graph of vertices and edges in the Voronoi diagram. It's edge-based, with each edge represented by two directed half-edges, one for each direction. This allows efficient navigation and manipulation of the diagram.
Wow, this is intricate. So, in summary, Fortune's algorithm is a powerful but complex algorithm. It's efficient, but requires careful handling of various edge cases and a sophisticated data structure for both the intermediate beachline and the final Voronoi diagram.
Precisely. While an O(n) squared implementation might be easier for most applications, understanding Fortune's algorithm provides valuable insights into computational geometry and algorithm design. It's a testament to the beauty and complexity of efficient algorithms. Thanks for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into the world of Voronoi diagrams and Fortune's algorithm. Goodbye.
Bye-bye.